Elena has obtained his master in cosmology astrophysics at Bologna University, and then has obtained a PhD from Max Planck Institute for Extraterrestrial Physics. And now, the past year, she obtained a position as a Minerva Fast Track Fellow at Max Planck Institute for Extraterrestrial Physics. And today she will talk to us on the molecular fractionation in star-forming regions. So please, Elena, go ahead.
Hi, everyone. Thank you very much for the introduction. Yeah, I'm Elena, and I am an astrochemist. And so today I will share my screen and I will talk about something very actually technical in the terms of astrochemistry, but I hope you will be able to enjoy it as much as I do. I just would like to say that I am very happy to give this talk in this series, because also, I mean, I did my undergrad, as you heard, in University of Bologna. I studied physics in Bologna, so taking part in such a nice series of seminars is really a pleasure for me. And also I see a lot of my former classmates and also a couple of professors of mine, I think, in the audience, so I'm very happy. So without further ado, I will talk about molecular fractionation in star-forming regions. So my main field of expertise is star formation, and in particular, galactic star formation. So we will talk about the Milky Way mainly, well, actually only in this talk. And the idea is that star formation is the story of the cycle of the interstellar medium, also known as ISM, where you start with the diffuse medium, diffuse clouds, which basically under self-gravity start to contract and start to get denser and denser. And within dense clouds, you can form dense cores, which are extremely cold and very dense, where the final act of the gravitational collapse can take place, therefore leading to the formation of a protoplanetary system, so a protostar surrounded by planets, well, protoplanets in this phase, and then a fully developed stellar system. And the cycle is closed because during their lifetime, and especially during their final stages of stellar evolution, stars gives back part of their material to the ISM, and they have important feedback of it, which closes the cycle. So the idea of star formation is to say something about this cycle. And the idea that I would like to give you is that fractionation processes are a very efficient and effective way to do so. So what are we talking about? The interstellar medium in its cold phase is composed by molecular gas, so it's full of molecules. H2 being, of course, the main molecule, but not the only one at all. And every element in the universe, well, most of them at least, have several stable isotopes. So you can form the same molecular compound, substituting one given element, one given atom with one of its stable isotopes. What you form is then so-called isotopologue, which shares a lot of properties with the main molecules, but not all of them, because if you substitute two isotopes, they usually have, for example, different spins, different masses, and all of these things will affect the energy level structure of the molecule, and therefore will leave some clear fingerprints in their spectra, for instance. So this process, when you substitute isotopes in molecular species through chemical reaction, is known as chemical fractionation. And all elements have some fixed isotopic ratios, in the sense that the relative abundance is somehow fixed, at least in a given space in space and time point. And these elemental values are either set by the primordial nucleosynthesis, so the nucleosynthesis that happened right after the Big Bang, or more frequently by nuclear reaction in stars, because the interior stars are the place where you form atoms, and then of course you form also isotopic mixtures. The fractionation types that I will discuss today and that I have mainly worked on in my career are, first of all, hydrogen fractionation, also known as deuteration, when you substitute hydrogen atoms with deuterium atoms, and nitrogen fractionation. Nitrogen is the fifth element for abundance in the universe, and it is present in two stable versions. The main one is the 40N, but there is also the 50N, which is way rarer, but still detectable in the interstellar medium. So the main question that many would ask is why I'm interested in this. And as I told you, the general ambitious plan is to use fractionation processes, since they are very peculiar, to say something about the origins of the different materials, for instance, in our own solar system, and in general, to trace back the link between the materials that form a planetary system with the primordial material that formed the cloud from which the planetary system was formed. And the idea is to use isotopic ratios of different elements in distinct molecular species to follow the star formation process. But if we want to do that, what we need is a complete understanding of the chemistry and of the evolution of fractionation throughout the star formation process, which is something which is still missing. And here is where let's say, I play a role, in the sense that I'm mainly an observer, and I do provide several observational data regarding fractionation that can help building these chemical networks. So the first project I would like to talk about is concerned deuteration. So we're talking about hydrogen fractionation here. And we will look at the deuteration maps of two very abundant ions, which are diazenylium and 2H+, and protonated carbon monoxide, HCO+, in a source which is Linden 1544, which is a sort of prototypical pre-stellar core, so a sort of prototypical progenitor of sun-like stars. Why these two specific species? Well, as I told you, this ion is quite abundant in the interstellar medium, and they are linked with very important molecular species, because N2H+ comes directly from N2, which is the main reservoir of nitrogen in the molecular gas, which unfortunately, as molecular hydrogen, lacks a permanent dipole momentum, and therefore is not observable in the cold gas. And HCO+, on the contrary, is formed from carbon monoxide, so CO, and is therefore linked to the second most abundant molecule in the interstellar medium. So, as I told you, on one hand, we want to use isotopic ratio as a sort of diagnostic probe of the star formation process, but on the other hand, deuterated molecules, because of their characteristics that I will show you in a second, are extremely good probes themselves of the cold and interstellar gas. So if we want to study these stages of the star formation process, deuterated molecules are very useful. And the reason why is that, well, of course, we're talking about the relation of deuterium to hydrogen, which has an elemental value, which is set actually, in this case, mainly by the primordial nucleosynthesis, which 15 minutes after the Big Bang produced some deuterium. This value was slightly changed during the universe evolution because deuterium is efficiently burned into the initial stages of stellar evolution. But it changed not much actually since the very primordial times. But if you go to the cold ISM, what happened is that you have the key production of the first deuterated ion, which is H2D+ through this reaction. And H2D+ is highly reactive because it's an ion, and therefore it starts the chain of all deuterated species, basically, at least in the gas phase. And the peculiarity of this chemical reaction is that it is very efficient at low temperature. Another way that you can enhance the abundance of a molecule, and therefore in this case of H2D plus and all deuterated molecule, is of course if you have a way to suppress its destruction pathways. And H2D plus as H3 plus are destroyed mainly by reaction with CO. And what happens when you have very high density and low temperature is that most of the CO molecules will start sticking onto the dust grains. They will form ice mantles around dust grains, and therefore they will be completely gone basically from the gas phase. And this is known as depletion or freeze out. And therefore, when you don't have a lot of CO around, you don't destroy that much H2D plus, and you can boost really deuteration. You can then understand why prestellar cores, so the birthplace of sun-like stars, so small of low mass stars, are known as deuteration factories because basically they are exactly characterized by this physical condition. They are very cold. We're talking about 7, 10, 12 Kelvin, and they are very dense, 10 to the 5, 10 to the 7 centimeters minus 3 in terms of volume density. And so you have some molecules that enhance their deuterium content up to 4 orders of magnitude with respect to the elemental value, as you can see here. So here I show a number of observational studies. The so-called elemental values set basically by the Big Bang is this dashed horizontal line. Already the water that we have on Earth in our oceans is enriched in deuterium with respect to this elemental value. And several solar system bodies such as comets or meteorites, for instance, they are also enriched. But if you go to prestellar cores and to species like ammonia, like NH3, you really can reach a deuteration level of 50%, so very high, which means that deuterated molecules are very good in traces this gas, exactly. And what I wanted to do with my project was investigate the deuteration distribution, so not just one value per source, but really a spatial investigation in a very well-known source, which is our L1544. And secondly, I wanted to couple these observations with some state-of-the-art chemical networks to say something about the chemistry of this source. And let's meet the source. This is Taurus. So Taurus molecular cloud, shown in dust thermal emission. This is PIRE data from Herschel. And Taurus is a very well-known close by site of ongoing low mass star formation. And we will focus on this very part here. And let's zoom in. This is Linden 5044. This is a prestellar core, so it contains around 10 solar masses, so it has the potential to form more or less one low mass star. It's quite isolated, so we don't have to worry about studying a very crowded environment, and it's also close by. So all of these properties made it a perfect target of a very huge campaign, both from the observational and from the theoretical point of view, in the last couple of decades, I would say. And we now know a lot about, especially its physical structure. We collected observations on L1544 with the IRAM 30-meter telescope, which is shown here behind myself. And we observed maps of diazenylium, as I told you at the beginning, and of protonated carbon monoxide in all these isotopologues. And we tried to collect as many rotational transitions as we could. And you will realize in a while why this is important. And so this is what the data look like when you do integrated intensity maps. So moment zero, you're probably more familiar with this term. As you can see, not only different species, but also different distinct transition of the same species present quite different morphology. And this is due to the distinct excitation condition that each J transition have. So the idea is that from all of this data, you want to build map of the column density of each isotopologue, and then from the ratio of the pair of isotopologues, you can derive the ratio of the deuteration level, the maps of the deuteration level, which is our objective. The standard way to do this is the so-called LT analysis. So the local thermodynamical equilibrium. So to briefly explain what I mean, these are the radiative transfer equation. You observe mainly temperature values, so you observe fluxes, and you want to go from these fluxes to the column density of the molecule using some spectroscopy individual, basically. The problem with this equation is that you have to take into consideration the excitation temperature of the transition. So a common way to deal with this problem is that if you observe multiple transitions, so you have multiple data points for TMB, you can, and you assume that all transitions share the same excitation temperature, which is the LTE hypothesis, you can fit the excitation temperature and the column density at the same time. The problem is that when you go to very cold gas and very narrow lines with very crowded hyperfine structure, this LT hypothesis is not good anymore. And what you need to do is that you need a fully non-LT approach, which unfortunately in our case for this work was limited in a sense only to the center of the sphere of the source, but that we managed to then use this analysis to really reconstruct the column density maps of the whole L1544. So how does a non-LT approach work? You need a non-LT radiative transfer code. In our case, I used MOLLI. MOLLI was developed by Eric Quito. And it's extremely good, especially for molecules which have very crowded hyperfine structures, such as the one that we are studying here. You need a fully description of your source, and by this I mean a density structure, a temperature structure, both gas and dust, a velocity structure if, like L1544, your source is, for instance, contracting under gravitational pull. And you need a distribution model for your molecules. And for this, we used the state-of-the-art gas-grain chemical network developed by my colleague Olli Sipilä. And all these data are given as an input to the radiative transfer code, which performs the radiative transfer analysis and gives you synthetic spectra that you can compare with observations. And unfortunately, or luckily, I don't know, you don't really have one abundance profile for each molecule because, first of all, the code is an evolutionary code, so you can stop the simulation at different evolutionary time steps. And on top of that, the core is not isolated, but is embedded in a medium and is embedded and is illuminated by some external radiation field. And since it's embedded in a cloud, this radiation field can be attenuated by different factors, which are the distinct colors that you can see in this plot. So my job was to try all these abundance profiles, plug them into MOLLI, produce some synthetic spectra to compare with the observation. And unfortunately, MOLLI takes very long integration time to converge, so we could not do really a full exploration of the parameter space, which perform a limited exploration of the parameter space. But we found what we consider the best fit solution for our set of lines of transitions, which are shown here. You have in red the model and in black the observations. And these are the H-bearing species, and these are the D-bearing ones. As you can see, not always we have a perfect agreement, of course, it is extremely difficult, but we have a general agreement with the observed fluxes and with the observed line shapes, of which we were very happy, actually. And these are the final abundance profiles that provide these best fit values according to the chemical network. And on the right panel, you have a zoom in of the left one. And the interesting thing is that all molecules here considered show a drop in their abundance. This is a depletion sign. And this is interesting because for some molecules, especially for N2D+, for instance, this is something that has been theoretically supported by many models, but for which there are very scarce observational confirmation, and we provided one, which was important. So from all this work, what you get are the column density maps, which are shown here, from simply the ratio pixel per pixel from the right panels with the respective left panels, you get the iteration maps. And here I show them for N2H+ on the left and ACO+ on the right. And I will take a minute to comment on this. So the black cross is the center of the core of L1544. And you can see that the two iteration maps have quite distinct morphologies, in the sense that the one of N2H+ peak right on top of the core center, while the one of ACO+ peaks slightly offset towards northwest with respect to it. And also, you can notice that the color bar have completely different ranges. You reach 26% of the iteration in diazenylium and only 3.5% in ACO+. And this is due to distinct chemistry that this molecule experiences. So ACO+, as I told you at the beginning, comes from CO. CO is an early type molecule that as soon as the gas starts getting cold and dense, when the iteration is boosted, it starts to be efficiently removed from the gas phase. On the other hand, N2H+ is a late type molecule, which is yes, still affected by depletion, but not to such an extreme extent. And therefore, it is very abundant exactly in the physical condition where the iteration is boosted. And this explains exactly what we are seeing here. So as a conclusion, well, first important one, we found observational evidence of the depletion of all the species of interest. We confirmed that non-LT analysis in this kind of sources is needed, basically. And finally, we found that the different chemistry that ACO+ and N2H+ suffers from, well, let's say are produced from, explains these observational results. I will now switch to the other part that I talked to you about, which is nitrogen fractionation, which is something that I deeply studied during my PhD and afterwards. And if one can have a favorite kind of fractionation, nitrogen is by far my favorite. And I will focus on N2H+. Why on this ion? The reason is what I told you before. N2H+ comes directly from N2, which we consider to be the main reservoir of nitrogen in the molecular gas, but that we cannot directly observe. So we use it as a proxy for the bulk of nitrogen in molecular clouds and dense cores. So the interesting thing is that nitrogen is present, as I told you, with the main form 14N and the rarer 15N. And the elemental value, which is shown here with this dashed, with this solid curve, is set in this case not, of course, by primordial nucleosynthesis, but by the nuclear reaction in stellar interiors, in particular the CNO cycles. And it's around 440 in the solar neighborhood. Already the N2 present in the Earth atmosphere is enriched in 15N with respect to this value, and this level is shown with the dashed line. But if you then go to the interstellar medium and you target different species and different environments, pre-stellar and proto-stellar ones mainly, you see values scattered over a really large range. And in particular, this value of 1000 is extremely high. It was measured again in our favorite source, L1544, and by my former supervisor, Luca Bizzocchi. And this was very puzzling when I started my PhD, because it is not consistent at all with what we believed in terms of nitrogen chemistry. So theoretically speaking, N2H plus fractionate through this equation, which is a simple isotope exchange reaction, and which, however, should not be very efficient in the cold gas. So you expect a bit of fractionation, so values slightly smaller or consistent with the 440, which is the elemental value. And this is not consistent with that data point, which of course is just one data point. So the first thing I did during my PhD was to target 3 more pre-stellar cores to increase the sample. And I will show you an example. This is another very well-known core. This is L183, again shown here in its dust thermal emission, as seen by Herschel. And we use the 30-meter telescope to observe N2H plus and N15NH plus, which are both shown here. As you can see, while the main isotopologue reaches 2 Kelvin in brightness temperature, the rarer one is at most 30 millikelvin, so basically 2 orders of magnitude less intense. And this is something that I really like about nitrogen chemistry, because 15N species are very rare, and so they require a lot of hours at the telescope, which is something that I enjoy a lot about my job. But beyond this, again, what we want to do is that we want to derive the molecular densities to derive the isotopic ratio, similarly as what I showed you. And to do that, we need an NLT approach, because we're talking about dense pre-stellar cores, very cold. So we need, I built the physical models of the cores using the Herschel data. I inputted to MOLE again the most recent spectroscopy data that were available. And in this case, I use a very simple chemical model to derive the molecular abundance profile. And after this analysis, you can derive the column density and the isotopic ratio. And here is again the example of the result in L183. As you can see, again, you have the observation in black and best fit model in red. The best fit is very good, both for N2H plus and for N15NH plus. And I could then produce these plots. I also recomputed the value for L1544 because of consistency. As you can see, all these points are inconsistent basically with the elemental value of 440. And this is a confirmation that indeed N2H plus is anti-fractionated, so it has less 15N than necessary, than expected. And this is the updated plot that I showed you at the beginning of this project. So, of course, one can ask why. So what is the theoretical reason for this behavior? And there have been 2 main possible explanations for this. One is the so-called Loison's theory, which was published by Loison a couple of years ago, which is based on chemical effects. So it's based on basically different reaction rates that N2H plus and its isotopologues have. While the other theory is the Furuya-Kawa one, which is based instead on photophysics. So it involves a process known as selective photodissociation. So my first idea was to test the Loison theory, and I will give you an idea of what it says. So basically, the idea is that both these species are destroyed either by CO or by free electrons, so by dissociative recombination. And the idea is that the reaction with free electrons has a reaction rate which depends on the isotopologue. So they change whether you have a 14N or 15N. And in the cold stellar gas, of course, you have no CO because it's completely gone, it's completely depleted. And therefore, you have only a reaction with free electrons that destroys more rapidly the 15N bearing species. And so the 14N over 15N ratio increases a lot. While in the warm protostellar gas, you start to have back all the CO because the temperature is slightly higher than 20 Kelvin. And therefore, this reaction with CO is the dominant one. And the 14N over 15N ratio goes back to the elemental value. So you should observe lower values in protostellar environments. And to test this, I targeted 6 protostars. Most of them are in the Perseus molecular cloud. This allowed us to avoid a bit of environmental effects. And from this table, what I would like you to focus on is that we are talking about sources with average temperature between 25 and 50 Kelvin. So definitely warmer than pre-stellar cores. And also, again, the game is always the same one. So you want to derive the molecular column density to derive the isotopic ratio. Luckily, in this case, LT approach, which is easier in this kind of sources, is enough. And this is because protostellar envelope are warmer and more turbulent. The lines are broader, and all this effect makes non-LT effects less important, less significant. So I fitted the observation with an LT approach, and I derived the isotopic ratio. And this is the final results. So here you have in blue dots, you have the pre-stellar values that I showed you a couple of slides ago, with their average as a dashed horizontal line, while the red stars are the protostellar values with their average shown as a dashed dot line. And as you can see, the two environments present values in 2 distinct ranges, and the average are totally inconsistent within each other. And the protostellar average is instead marginally consistent with the elemental value. So we try to see whether this quantity, this isotopic ratio, showed some trend with other quantities, in particular with the dust temperature, because this should be a temperature effect, and also with the depletion factor of CO. Unfortunately, we couldn't find any significant trend, but we need more data to have a consistent sample of measurements on these quantities. And so our data show that indeed protostars show significantly less, smaller isotopic ratio values with respect to pre-stellar ones. This hints that the Lozon theory is the correct one, but we need more data, in particular in terms of dust temperature and gas temperature measurements, to really conclude, say something conclusive about this. And if I still have a couple of minutes, I just wanted to show you one last project. This is basically the last project I led, and it does not deal with fractionation, but it does deal with deuterated molecules. And I want to use it as a way to show you how powerful deuterated molecules can be. And here are ortho H2D+ observation of high mass clouds. So ortho H2D+, or H2D+, let's simply, as I told you, is the first deuterated molecule in the gas phase, and it is very abundant only when the gas is cold and dense, because as soon as the temperature rises above the desorption temperature of CO, so as soon as you start releasing CO back into the gas phase, it reacts very quickly with H2D+, and the latter abundance, the abundance of the latter drops. So if you see ortho H2D+, you can be pretty sure that you are looking at pre-stellar gas. And this is very interesting for high mass star formation, because with respect to low mass counterparts, the formation of high mass stars is still poorly known, because mainly high mass stars are rarer, they are on average more distant, they are way more short-lived, and so they are again rarer intrinsically, and they also form in very crowded environments, which are difficult to disentangle. So in particular, the very early stages of the pre-stellar phases are still poorly known also from an observational point of view. So we target 2 intermediate mass clouds, which are shown here, using, they are quiescent, so they are not bright, both at 24 and 70 micrometers, which is a good hint of the fact they are still in a pre-stellar early stage. And they were observed with ALMA. The PI of this project is Stefano Bovino from Concepcion in Chile. And they observed both the dust thermal continuum shown in color scale and the H2D plus transition in band 6, in band, oh my God, at 370 gigahertz, which is shown with the contours. And as you can see, H2D plus is quite abundant. It's not concentrated in spots, but it's very well distributed on the whole clump, which was already a very interesting result. But what we could do is that we used the ortho H2D plus data to identify pre-stellar cores, which are shown here with the contours, and which we know, as I told you, because of the chemistry of these molecules, that are truly pre-stellar. And in particular, this number 2 in the right panel in AG354 could be as massive as several tens of solar masses. And this could be really a very good candidate to be a high mass pre-stellar core, which is something that has been hunted for heavily in the last years. So I just wanted to show you these few slides to tell you, to let you know how good is deuterated, especially deuterated light species like H2D plus, to probe and to investigate the pre-stellar gas, and how you can use it to effectively look for and even find high mass pre-stellar cores. And with this, I have finished. So I thank you very much for your attention. I hope I could make you a bit understand what fractionation is if you're not from the topic. And if you have any question, I will be happy to answer.
Thank you, Elena. Very, very, very interesting. And I ask people to, if they have questions, to raise your hands.
I will stop sharing for the moment, but then I will go back to the slides.
Perfect. If you have questions, please raise your hands. And in the meantime, we can ask Elena if it was important for you to win the Minerva Fast Track Fellowship from Max Planck.
Yeah, it was an honor, honestly, and it was I didn't even expect it, honestly, but it made me. It is important, I think, to be part in the change that we all hope for, which is increasing the female fraction in STEM career in general, in astrophysics as well, and taking part in such an initiative from the Max Planck Society in this case was, I think, a really good experience. And I have now 2 female PhD students.
Good, very good.
And I hope that I can, with the little that I can do, I hope I can keep pushing in the right direction, because it's very needed, I think.
Yes, I agree, of course. In Italy, maybe we have a lot of girls that study in astronomy, for at least, but it's needed also in the other countries to increase the number of people that obtain PhD, female, of course. So
yeah,
this is important.
Yeah, and also to provide the environment for them to continue, because that is,
yes, absolutely.
we see a lot of PhD students from both genders, but then as you go on and on, the differences start to increase. And I think it's also a matter of time, right? You have to wait for new generation to grow.
yeah, sure. Okay, if there are questions, please, this is the moment. I have a curiosity. You say that you're in the last part of your talk that this is a good way to search for very massive pre-stars. So you think that this way can help to find more, or have you in progress some search for this kind of?
Yeah, so the idea is exactly this. So the problem with this, in this data that I showed you, we found only one basically quite massive, so 30 solar masses or more core, but on the other hand, we targeted intermediate mass clumps. So these are not very big. We're talking about 150 to 200 solar masses in total when observed, like with the apex. We believe that targeting really more massive, like thousands of solar masses, which of course statistically host more seeds of high mass stars, then we could really see a population of high mass cores, and which would be very interesting, because then again, as I told, if you see H2D+, you're pretty confident that no protostar is already embedded, which is not something that you can tell simply by looking at the dust thermal emission. If you see peaks, it could be simply overheating due to protostellar feedback.
Okay, yes. And another point is that there is any connection of, for example, the clouds, that the first cloud that you show that you have so high values with respect to the other you studied. There is a connection with the position of the Milky Way or not?
In a sense, yes, but it's taken into account in the sense that, so for those isotopic ratio that depends on stellar evolution, like nitrogen, oxygen, there is a galactic trend, because of course, since it's not the whole Milky Way is coeval, you have a trend, and then you can take this into account, because you know, I don't, but people know stellar evolution well, and so they can predict the elemental values that are used as a sort of initial values then for the chemical networks, because then the chemical networks evolve from this initial condition.
Okay, and now there is Christian Vignali. Please talk.
Ciao Elena, I have a curiosity. At the end of your talk, you said that you will need more data. Can you be more specific on the kind of data and facilities you need to shed light
on nitrogen, you mean, or
yes.
So the kind of data that we would like is that, so to really say that this is the chemical effect that we are seeing, it would be very great to really see a trend also with the temperature, because as you heat more, you release more CO, you destroy more N2H+ through CO, and so you should see a trend. The problem is that we have access to dust temperature measurements, which however come from different telescopes. They were obtained with in different ways. So I would say that either we need some definite assessment of the dust temperature in a consistent way. So I don't know, if I guess that there are Herschel data of all these. Well, there is Herschel data of Perseus, so this is already there, should be reanalyzed. Or you can go to gas temperature and then use like ammonia, for instance. And then I don't think that there are, no, the data are there actually, but still they need to be completely analyzed.
Okay, thanks.
Any other question? Seems not. Okay, so we thank Elena for the very interesting talk, and we give you the next appointment, which is in September, because we stop for summer, and next colloquium you will find the next speaker in our webpage. Many thanks to all, and thanks again, Elena.
Thank you very much.
In 2 months.
Thank you very much. Bye.
Bye-bye.
Bye.